So we've got this implicit differentiation stuff figured out. The main thing that we've got to worry about is product rule and chain rule and all that kind of stuff. Which variable is the input, which variable is the output. If you haven't yet, go read the little introduction to this video because I think it's pretty important to show this example off. And what we're going to do is we're going to differentiate this like we would for implicit differentiation using the d over dx operator. That's the derivative of. But notice that there's 3 variables now. So we're going to see how things work with all 3 of these things. So our equation now looks like the derivative of x squared minus the derivative of natural log of y plus the derivative of z to the 4, and that's going to equal the derivative of 10. And most of these are going to work out exactly like they would if this was just a regular old implicit differentiation example. The derivative of x squared is 2x. For the natural log of y, we've got to do some chain rule, so we're going to have 1 over y times y prime. Or if you want, you can just go ahead and say, really, it's just y prime over y. I'm going to skip this middle one for a second and just figure out this derivative of 10. That's 0. Let's come back to this. Here, if we're trying to look at the derivative of z to the 4, we're going to notice that since z is not the same as our variable here, this is going to act like a function as well, just like y. So we're going to do the same kind of thing that we would do if this was a y. We're going to do chain rule on it. We're going to do 4z cubed z prime. If we wanted, we could have written this using differentials, and I think it's really important to see that in this example just to see what's going on. So let me rewrite this out, except instead of y prime and z prime, I'm going to use dy over dx and dz over dx. So we've got 2x minus 1 over y dy over dx, that's y prime, plus 4z cubed dz over dx, that's z prime, equals 0. So again, notice with the y and the z term, we had to use the chain rule. So what related rates is going to do is it's going to take an equation like this that has different outputs related to each other in that equation. And when we differentiate it, we're going to get the derivatives of those outputs because we have to use the chain rule. So this is the derivative of y. We say with respect to x, where x is the variable. This is the derivative of z, where x is the variable. So this little dx part in the bottom of this differential really tells us what acts as an input, and then every other variable is going to act like an output. So if we were looking at d over dy for these, then we'd have to do the chain rule on x squared, and our derivative would be 2x x prime, or you could say like dx over dy. D over dy of natural log of y, or the derivative of this, where y is the variable, would just be 1 over y, because now it's not an output. And then similarly, we'd use a chain rule on this, except instead of dz over dx, it'd be dz over dy. So the bottom part of this differential notation is, again, super important. And that's pretty much it. From here on out, you're just going to be solving some kind of application problems. This is a classic one that comes up in about every calculus class. If you make it through a calculus class and don't see an example like this, oh, and there's a typo here. This is supposed to be 20 feet. I changed that so you can see it here. If you don't see an example like this, then that's pretty rare. Anyways, here it is. We've got somebody up here cleaning their gutters, so they're standing on the ladder here, and we've got like the rest of the house. Oh, that's terrible. We've got like the rest of the house here. There's their roof. So this is what they look like. So they're up here cleaning the gutter, and they set the 20-foot ladder, so that's this length here, up against the house, 6 feet away from the house. What happens is that the ladder starts sliding away from the house. It starts moving this way. As it moves that way, it's pretty clear that our ladder is going to slide down, right? It's going to end up looking like this, and then like that, and then it's going to fall flat. So as this bottom moves farther away from the house, the top of our ladder is going to slide down our house. These are pretty ugly diagrams, but you get what I'm saying. What we want to know is if this is sliding away at 2 feet per second, then how fast is the top of the ladder falling, or what's the speed at which the man on the top of the ladder is going to fall. What's kind of cool here is that we don't really need to take gravity into effect, because really that's kind of built into this bottom sliding part here. Gravity is pulling our ladder down and pushing it away from the house at the same time. There's some coefficient of friction and blah, blah, blah. This is not a physics class, so I don't really care about any of that stuff. All we know is somehow we were able to find out that it's sliding away at 2 feet a second at this instant, right like that. All right, so let's see what we know. We can fill in some other information if you'd like. You can fill in this b value, the height of the house here, by using the Pythagorean theorem. Notice that we have a right triangle, so we know that a squared plus b squared is equal to c squared. So if we wanted, we could solve for b, and we're going to get the square root of 200 squared, which is 400, minus 6 squared, which is 36. That is the square root of 373. I'm not sure what that is. Let's see if we can get an approximation for that. I'll bring up my calculator. Here we go. And we'll say square root of, what was it? 373. So approximately 19.3. Let's just say that. So 19.3 feet up in the air. What you'll notice is that when we did this, we have this little equation that connects A, B, and C. And if you want, we could go back and take this rate of change that we have, and we can notice that that's A changing. And the variable at which it's changing is time, because it's feet per second. A is measured in feet, and so the variable at which that feet is changing is time. So this is really dA over dt. It's the a variable changing with regard to time. That derivative now is 2. I'm going to say it's positive because a is increasing. It's getting longer. It's sliding away from the house. So now, when we're trying to figure out the speed at which the man falls, what we're really looking for is another derivative. And we're looking for this rate of change. We're looking for how fast does the b side length change. So we have a relationship between A, B, and C, and we want to come up with dB over dt, the derivative of B with regard to t. What we can do is differentiate. Maybe I'll see if I can type this out here. We're going to differentiate everything with regard to our variable t. So we're going to take this equation and differentiate the whole thing. Oops, let's leave that as blue, and now I'll change back to my pencil. All right, so let's go and get a clean slate on this. We have a squared plus b squared equals c squared. And what we want to do is find the derivative of a squared plus the derivative of b squared, and that's going to equal the derivative of c squared. And we can find all these derivatives. Notice on all of these, A, B, and C, they don't match up with our input variable t from the bottom of that differential, and so we're going to have to do the chain rule on all of these. So we've got 2a times the derivative of a. You could say a prime, but I'm going to use the notation to keep reminding us what our input variable is. The derivative of b squared is going to be 2b times dB over dt. And finally, 2c times dc over dt. At this point, I think we've got everything we need. Let's just remind ourselves. We had said that A, I think, was that the base? Yeah, that was our base, so that's 6. B, we said, was 19.3 using the Pythagorean theorem. We found that. C, we found to be 20 because that was the length of the ladder. And we had this rate of change here, which was how fast the base was changing. That was dA over dt. And we want to know dB over dt, and we'll also need to know dC over dt, because we've got that in our equation as well. Let's go back and let's see how quickly C is changing. Notice that C is the length of the ladder. So take a second and think about this. How quickly is the length of the ladder changing as it falls? You probably realize that it's not. our ladder stays the same length. It's a constant. And so what we can say is that that derivative is 0. At this point, we can just plug and chug. We're going to put everything in place. So we've got 2 times 6 times 2 plus 2 times 19.3 times dB over dt equals 2 times 20 times 0. 2 times 6 times 2, that's going to be 24, plus 19.3 times 2, that's going to be 48.6. Is that right? No, that's not right. It's 38.6. There we go. Times dB over dt equals 2 times 20 times 0. That's 0. Now we can solve this thing for dB over dt by subtracting 24 and dividing by 38.6. So over here, I'll do this. dB over dt is going to be negative 24 over, that's a 4, there we go, 38.6. And I don't really know what that is. And that's, let me just bring up my calculator again and see if we can figure out what that is. So I've got negative 24 over 38.6. Approximately, I'll use these approximate signs. Oh, and what was that? Negative 0.622. Negative 0.622. And the units is in feet per second. Now, here's a question. Why is it negative? Well, if we go back to our picture, we'll remember that he's sliding downwards. This length is getting smaller. That means it's decreasing. That means it should have a negative rate of change because every second the height is getting smaller and smaller and smaller, close to 0 where he hits the ground. So he's falling at, you could say, the speed is 0.622 feet per second, and the velocity is negative 0.622 feet per second because velocity takes sign and direction, into consideration. So again, all we really did was we differentiated our equation that we had, and we just had to use the chain rule on pretty much everything. So I don't really care a ton about those geometry problems. There's a couple of them in the book that you can look at and get some help with, and most of them require just kind of drawing some pictures and setting some things up and using either the Pythagorean theorem or sometimes things like area of a circle as it expands and blah, 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 and we just differentiate that equation. But what we want to do is apply this to cost, revenue, and profit. And I think these examples are a little bit easier, and they're more in line with what we're going to care to kind of think about because these are the applications we're going to soak ourselves in this semester. So here's our example. We've got some sort of a company that's manufacturing and selling HDMI cables. They've got a cost function here. They've got a price-demand equation. Remember that little p is price, not profit. So that means that for X number of items, we've got some sort of a price that they can charge. And X is the production of those HDMI cables per week. So we're looking at weekly production. Let's say that currently they're producing 2,000 of those cables a week, and they decide to start tinkering with their production. They're going to try increasing their production by 100 cables per week. What we want to do is find out the instantaneous rates of change in cost, revenue, and profit per week. And we're looking at those things per week, so we're looking at them as dC over dt, dr over dt, and dp over dt. This is an example where I want to steer clear from using the prime notation because if we were to say C prime, that makes us think of marginal cost, which is how the cost is changing per unit that changes. This is changing per time unit, T. So I want to just be careful about that. So don't use that prime notation here. It's really easy to get it mixed up with marginal cost, marginal revenue, and marginal profit when that's not what we're referring to here. We're talking about what happens as the time unit marches forward. This differential notation is really helpful because it has that flexibility, but it does take a little bit of getting used to. All right, before we start anything, we should come up with our revenue and profit functions. If you remember, revenue is price times quantity, X times P, where P is that lowercase p here, that's price. So we've got X times 30 minus 0.005X. So we've got 30X minus 0.005X squared. And profit then is revenue minus cost. So we're looking at our revenue function, 300x minus 0.005x squared, minus our cost function. And again, we'll remember that we've got to put this stuff in parentheses so that we actually do subtract 8 from this. Oh, I put 300 here, and that's supposed to be 30. Sorry about that. I just misread the line above. Let me fix that. There we go. All right, so now we'll go ahead and actually subtract these things. We've got negative 0.005 x squared plus 30x minus 8x, so that's 22x, minus 1,200. So here's our revenue, here's our profit. What we can do now is find these derivatives with regard to time. So this is how we'll do this. We're going to say dc over dt is just the derivative of the total cost function, which we said was 1,200 plus 8x. Notice that we're looking at the derivative with regard to time, so x is going to be a function. So we're going to look at the derivative of 1,200. That's going to be d over dt of 1,200 plus the derivative with regard to t of 8x. The derivative of 1,200 is going to be 0. The derivative of 8x is going to be 8 times, sometimes people will say x prime. What I'm going to do is just write this as, maybe I'll do this over here. I'm going to use that differential notation, 8 times dx over dt. For revenue, we can do the same thing, but before we do that, let's go back and figure out what dx over dt actually is. Here, we were told that we're going to increase the production by 100 HDMI cables a week. If production is the thing that's increasing, that means X is the thing that's increasing. And if we say that it's increasing, then we know that that's talking about a rate of change. So here, we're saying dx over dt is 100. So what we can do now is take this dx over dt and plug it in here. So we really have 800 for our cost. So our cost is increasing by $800 per week. Let's check out revenue. We're going to look at the derivative of our revenue function is 30x minus the derivative with regard to t of, was that 0.005x squared? Let me just double check. Yeah, okay, cool. So we can take a derivative of both of these pieces. Here, we've got 30 x prime, or I'll just say dx over dt, because again, x is acting like a function now, because t is our variable. And here we've got to do some chain rule, so we'll bring the 2 out front, so it's 0.01x, because our exponent subtracts 1, and now we'll multiply by the derivative of x. So in this one, when we go ahead to substitute things in, we're still going to be putting in, I'll maybe write this off to the side so I remember it. Dx over dt was 100, but we also need to figure out what x is. Well, here it says that currently our production is 2,000. So currently x is 2,000, and that's without changing anything. So what we'll say is that x is 2,000. Just like we had a height and a length of our ladder and a width away from the house and all that kind of stuff, and then it changed. Here we've got a production level before it changes. So we're going to put in 100 for x. We're going to put in 2,000, or 100, sorry, for dx over dt. We're going to put in 2,000 for x, and let's see what we've got. We've got 3,000. That's 30 times 100 minus 0.01 times 2,000, that's going to be 20 times 100, that's going to be 2,000. So we've got $1,000 per week. So cost is increasing at $800 a week. Revenue is increasing by $1,000 per week. You can probably guess what profit's going to do. It's probably going to be going up by $200 a week. Because if revenue is going up 1,000 and cost is going up 800, they offset each other, but there's a difference. So this ends up being the derivative of revenue minus the derivative of cost. But let's just find it anyways, just to get some more practice. Feel free to pause the video, go grab your profit function from before, take a derivative with regard to t, and make sure that it matches up with that 200. All right, let's see what we've got. Profit is, I'm going to have to flip back and forth a couple of times to remember this. I'm looking at the derivative of negative 0.005x squared plus the derivative of 22x minus the derivative of 1200. All right, so we've got more chain rule here. Notice that this is the exact same thing as what we had going on here. So we've got minus 0.01x dx over dt plus 22 dx over dt minus 0. So if we plug everything in, this term here is going to be 3,000. If we plug in 100 for x and 2,000 for x and 100 for dx over dt. Sorry, this is going to be 2,000 because that's that subtracted term over here. And this will be 22 times 100, so that's 2,200, and that was a negative here. So, sure enough, we get $200 a week. Now, again, this is not what the profit is. These are increases or rates of change. So that's an increase, that's an increase, and that's an increase. Every now and then you'll find that profit might end up being a negative, which means that profit is going down, which means that cost is increasing more than profit, which would be a bad deal. But here, we're saying that if we're currently producing 2,000 of these cables and we want to, we can increase our production by 100 cables a week, and that's going to increase our profit weekly. So not just our profit based on the number of items that we're selling, but based on that time unit, we'll be increasing $200 a week, which is a nice thing to know because most of our kind of finance budget stuff is going to be based on weekly or monthly expenses. And so these kind of figures are really nice for us to get at these changes per time unit. Anyways, again, the main key here is that all we're doing is we're differentiating things, but we're keeping t as a variable now for time. And so x now acts like a function, and so we have to do the chain rule on it, just like we did with y in implicit differentiation. That's everything that we've got. Jump through into the text and check out some of these business type examples. There's a couple where we can make the price-demand equation change with time and things like that, and it's the exact same concept. So try a couple of these examples, mess around with them. Let me know if you've got any questions, but that's the last topic that we're going to talk about in this unit. So good luck in preparing for the exam, and let me know if you have any questions. Thanks, everyone.